The graphical method is one of the most powerful methods to analyze a truss system, but 99% of students fail at it because of one or two easy to miss steps that I'm going to highlight today, and I'm also going to show you how to fix them if you make these mistakes. So to start, we're going to calculate our reaction forces, and we're going to take our pivot point right here in the bottom left corner at R2. And the only force we have to consider is this 5 kilonewtons. Now 5 kilonewtons from that point, its perpendicular distance is going to be 3 meters. So what we'll have set up is our clockwise moment equals our counterclockwise moment. And the 5 kilonewtons is trying to rotate clockwise. So we do 5 multiplied by our 3 for the perpendicular distance. So that's this 2 meters plus another 1 meter right there. Now the next force that we have is our R3, which is trying to pivot counterclockwise. So R3 is going the opposite direction. So we'll just simply have R3 multiplied by 2. And what we have left is 15 divided by 2, and that's R3. So our value for R3 is equal to, and that's 7.5 kilonewtons. So that's R3 done. So for our reaction forces, we're going to say that the sum of our vertical forces should be in equilibrium. So with that, we should see where our R2 plus our R3 for the reactions, they should be equal to that external force that's going down, which is our 5 kilonewtons. And we've already calculated our R3 value, and we know R3 to be 7.5. So R2 plus 7.5 is equal to this 5 here. So what we're gonna have left then for R2 is negative 2.5 kilonewtons. Now this negative 2.5, it's significant in the sense that we normally get our reaction forces to be going upward, but because this is an overhanging force that we have right here, then that's why we get that negative force. So this reaction over here at R2, it's actually going downwards, whereby R3 is going upward. And this is going to be very significant when we do our diagrams, which is what we're going to move on to now. So this is our bottom left corner. And because we know what R2 is, which is negative 2.5 kilonewtons, then we need to just input that. Now, what we don't know is CE. So we're going to assume that CE is going that way and BE is going that way. Now, this is where the first mistake usually happens, where students don't understand how to determine whether a member is compressive or it's tensile. Now, this is how I would like you to think about it. So I'm gonna annotate here before I do the question with you. So think of this line connected by those two dots. And I'm going to give you an instance where at the end of each of these dots, we have something pulling that way. Now, in order to balance this force going to the left, we need to have a force that's equal and opposite, and it's going to the right. Now, in this case, if our arrow is pointing towards the joint, and by joint I mean at the end right there, if the arrow is pointing towards the joint, then this entire member is meant to be compressive, so it's going to be negative. Whereby if we do the opposite now, so let's say we still keep our two dots at the end, and then we're going to connect that line to represent a member, and let's say this is the direction of the arrow. So the arrow is now pulling away from the joint. So in this instance, what we're going to say that this joint, it's actually in tensile, so it's positive in that case. Now this will become a lot more significant when we start to do our diagram. So let's draw our first force polygon, and to do this you need 3 key things in order to start. Number 1, so this is one of the mistakes where we don't know where to start. So the first thing that you need is you need to know what the magnitude. So you need to know what the magnitude of that member is, meaning what it's for. So do you have the value for the force there, force for that member? So that's the first thing. The second thing is we need to know the direction. So we need to know the direction that that member is going in. And lastly, we need to know the angle. So those are the three details that we need, and we can't neglect any of them, else you're going to get some mistakes that you can't fix. So let me show you how to determine your starting point now by just checking off each of these three. So when we look at member CE right here, the arrow is pointing upwards and away, but we have just assumed that. So we always start with the assumption that the arrow is pointing away. Now, we don't know its magnitude, so we don't know what force that member is carrying, so we can't start with that member. So you have to remember that. We do know its angle because the internal angles here are all 60 degrees, so we do know its angle, but we don't know its magnitude, so we can't start there. And the same thing happens now with BE. We don't know its magnitude, we do know its angle, but we can't start if we have only two of these. We have to have all three, so we need to check all three boxes there. So the member that will check all three boxes now for this is actually the reaction force, R2. So we know that it's going downwards because that's the negative 2.5 that we got, so that's going down. The 2.5 kilonewtons is representing its magnitude, and its direction, we already know it to be going down, and it's vertical. So the vertical suggests it's at 90 degrees to the horizontal. So we know all of those things. So we are going to start with R2. So what we have to set up now is our scale. So what I'm going to use for this scale is 2 centimeters to represent 1 kilonewton. Now you will need to use your ruler and your protractor for this in order to get it perfect. So I'm going to draw the first line now for my 2.5 kilonewtons. So that's going to measure 5 centimeters. So I'm going to start with that one. So that's approximately 5 centimeters right there. So 5 centimeters. So that will be representing my 2.5 kilonewtons. So what's happening now is I'm going to try to connect the other two parts. So you are going to draw a lot of reference lines actually. So the first line I'm going to connect to this is the horizontal member, BE. So that's going to be going across like so. So that's my horizontal member. Notice I am not too fussed about the length of it at this point. The good thing is you know what that line measures, which is your 5 centimeters, so that's critical. So now what's happening is you need to connect line CE to close this shape, and there is something crucial that you must get. So I'm going to show you what that is now as soon as I close that shape. So there we go. So that shape is closed. So this is the crucial bit that will cost you if you don't get it right. So right here is meant to be 60 degrees. And that has to be the case. You can't have the 60 degrees right there. And I'll show you why. And of course, right there is 90 degrees. So the reason why you can't have the 60 degrees right there is if I'm to label this right here is my BE. And this right here is my CE member. And if you look at how BE and CE connects right here, right there at the top, I'm looking at the joint right here. BE and CE connects at an angle of 60 degrees. So therefore, if you get this part wrong, the entire thing is going to be incorrect. So in terms of our measurements now, CE turns out to be, let's get that, 5.8 centimeters. So that's 5.8 centimeters for CE. And BE turns out to be 2.9 centimeters. And of course, because my scale is 2 centimeters to 1 kilonewtons, what I'm going to do is to divide my centimeter measurements by 2 in order to get what my actual magnitude is. So with that, CE, when I divide 5.8 by 2, CE would give 2.9 kilonewtons. And when I divide my 2.9 by 2 for BE, BE is going to give 1.45 kilonewtons. And we already know that the R2 is negative 2.5 kilonewtons. So we have one last thing to do now before we finish off this, and it's to input our arrows. Now this is so critical because this is what's going to determine which of our forces are negative or positive. And where you start is with the direction that you already know. So we do know that this member, that vertical member, it's going down. So that's why this arrow is going downwards. And what we have to do next is onto the next member, it's going to trail in the same direction of that first arrow. So I'm going to do that now, like so. And onto the next, same direction, like that. Now, you remember earlier when I said to you that the direction of the arrow will determine whether or not we are compressive or tensile. So what we do now, you will notice that BE arrow on my scale diagram is going to the left. So up here, I'm going to insert that to the left as well. You will notice that my CE arrow is going up or away from the joint. So this is going in the same direction like that. And how I determine now whether my force member is negative or positive. So CE, you notice that that arrow, it's going away from the joint. So what that means is this one here, CE, is a tensile member, so it's positive. But for BE, the arrow is going into the joint. So for BE, it's going to be negative. So BE is a strut. So that's how we determine which one of these members are negative or positive. So this one is done. Let's move on to the next joint, and we're going to go to the top left joint. So we're now at the top left joint, and the first thing that we're going to do is just input the previously calculated force members. So we just got 2.89 for CE. So let's insert that. So 2.89 kilonewtons, and that's for CE. And we can also insert our arrow as well, because we know that that was a tensile member, so the arrow will be going away from the joint. And things will get a lot quicker now. So let's get this member sorted. So our first step again is to identify which of our member we got the magnitude, the direction, and the angle for. So we already know that all our internal angles are 60 degrees. So that just leaves us with one member to start with, and that's CE. So I'm going to start with CE now. So of course our scale remains the same, and what I'm going to do is to start with a reference line. But this reference line is actually going to represent one of the members that I've got, because you notice that DC, so when I say DC, it's right here, DC is actually an horizontal member. So that reference line is actually going to represent DC. So I'm going to do CE now. So this angle here is 60 degrees. And we actually know the length of CE. So this is representing 5.8 centimeters. Now, the next force member, we know that all our internal angles are 60 degrees. So if you notice right here, CE, right there, I'm talking. So I've just drawn this arrow right here. That's where I'm pointing. CE and DE, they meet at 60 degrees. So if I'm to just draw or connect these two now, so when I connect those two now, so right here, what we have here is DE. This was our CE that we started with. So that's DE, CE. And our horizontal member is representing DC right here. So that's it. And when we measure these now, because all of these internal angles are 60 degrees, then what we expect to have is an equilateral triangle. So the most critical thing here to do then is to figure out if our member is compressive or tensile. And I'll show you how to do that again. So we're going to trail our arrows around now, starting from our known direction, CE. So CE arrow goes there, and it's going to go in the same direction around, like that. For DC, notice that this one, it's going away from the joint, like so. So DC going away from the joint. But when we get to DE, this arrow will be heading in that direction, so it's going towards the joint. And from what we have done at the start, you will know now that what's tensile or what's positive here. So CE, we know that from before, so that's 2.89 kilonewtons, and that's tensile. DE, that's going towards the joint, so that's going to be negative 2.89 kilonewtons. That's compressive. And then what we have left is DC, which is going away from the joint, so that's 2.89 kilonewtons. That's tensile member. Now, just before we go on to the last joint, if you could give the video a thumbs up and subscribe to the channel, I'd be really grateful for that. So now to the final joint, and we're going to use all the information that we gathered previously to do this one. So we only have one unknown member as well, and CD was going that way, so we input that, and we already know its magnitude, so we can go ahead and start our diagram. So let's start this one off with the 5 kilonewtons, which will measure approximately 10 centimeters on here, and then our CD measuring 5.8, so that's around 5.8 centimeters, and then finally we'll just connect these. Now, we know that 5 kilonewtons, it's a force that's going downward. So if we input our arrows now to begin with, we know that that would be going downward, like that. We know that this now will just trail around, like that, and going back in, like that. And if you notice, this 5 kilonewtons, it lines up perfectly with the same direction as CD. So for our AD member, this arrow will be going inward, like that, to the joint. And when we measure AD, that's 11.6 centimeters. So to convert these now into forces, we'll have AD equals 5.8 kilonewtons. And we already know what CD is. So that's all of the force members calculated. Now, if you'd like to see me do the method of joint for this exact question, just let me know in the comment. Or if you'd like to watch this next video right here on the method of joint, then you may do so. So I'll see you in the next video.